Welcome to lecture 19. Today we'll be covering the energy theorems, the second Castigliano's theorem, which is covered very thoroughly in my book. But before I get to that, I want to really emphasize what we're trying to accomplish in this course. This course provides the fundamentals to finite elements and actually other techniques as well. And before we tackle the idea behind finite elements, what we've done so far is to teach you some mathematical concepts like calculus of variations. And what calculus variations is really doing is if you can couch a physical problem so that you have a functional, and that functional depends on a function. And if I'm able to couch it that way, perhaps I can find the function that extremizes that functional. And perhaps when I extremize the functional, that will have a physical meaning for that physics-based theory that we're talking about. So there are various functionals in various areas of expertise, including heat transfer, fluid mechanics, and structural mechanics. We chose structural mechanics because it has a complexity of close to 15 equations, 15 unknowns, or the theory of elasticity. And, and it is really nice to see how it's applied there because you can see the idea of calculus variations really showing up everywhere. One of the first applications I showed you was a principle of virtual work. The principle of virtual work is a very general theory and allows you to develop structural theories. And you saw how I developed the 3D theory, and it's incredible to me, even to this date, after teaching for so many years. It's so exciting to me every time I develop the principle of virtual work for 3D, because when you calculate and you determine the Euler-Lagrange equations, those Euler-Lagrange equations are the equations that show up when I try to do through the integral form of Newton's law, which is extremely exciting to me to get it in a different way altogether. And from there, I then applied it to beam theory. I developed the beam theory for Euler-Bernoulli beam and Timoshenko. I developed it for axial bar. It was very exciting to see how those equations that came out are the same that you may have learned back in mechanics of materials. So extra excitement there altogether. And then from there, I took the principle of virtual work and specialized it. I specialized it for a case, and that case is the total potential energy theorem. And I was able to make that specialization by taking the most general theory, which is the principle of virtual work, and making two fundamental assumptions, which is that the deformation is conservative. The deformation goes through a conservative deformation process, meaning that the body of material, when you load it up and you remove the load, it will come back to the elastic. It will be fully elastic. It will come back exactly where you started before you start applying the load. So that's one of the biggest one. The second one was that the loading is conservative. With these two assumptions, I was able to develop something called the total potential energy. And using total potential energy, I demonstrated that if I were to minimize that functional, which is the total potential energy, that the equilibrium, the Euler-Lagrange equations happen to be the equilibrium equations, and that the displacements that satisfy those Euler-Lagrange equations are the ones that render the system in equilibrium. I demonstrated that through another problem, another Euler-Bernoulli beam problem for moderate strains, and it was very exciting to see how that works out. And that the equations that came out are the ones that you have seen already in one of the problem statements, which was extremely exciting to see. We also talked about how the total potential energy, that functional is a minimum. If you were to find it, if you try to find the stationarity conditions, you will find as a minimum. And a lot of you ask me, well, how do I get that done? Well, it will be very exciting if you can show me how it's done. And then we developed from the thermal total potential energy, I specialized it further. And what I did there was as an idea, and that was the first Castigliano's theorem. In the first Castigliano theorem, what we did, we further simplified the thermal total potential energy. And we simplified it by perhaps looking at, hey, what if I'm interested in a load somewhere in the structure? and the deflection corresponding to that. Well, we found if I took the strain energy and the total strain energy of the system and took the derivative of that respect to the deflection, that you will get the load. And so that's a great way of maybe solving problems in a very simple way. From there, I covered the Betti's reciprocal theorem that to me is also extremely exciting because it's very incredible how you can find deflections with very little information. Basically, I invite you, if you haven't seen that lecture, to really go through that. It's actually very exciting. And then from there, I draw a line in your head, draw a big line in your head, and I transferred over now to the complementary principle of virtual work. In the complementary principle of virtual work, I'm varying now the tractions and the stresses and the body forces. Those are the quantities I'm varying, while in the principle of virtual work, I was only varying the displacements. So now I'm looking at a different way of approaching the problem. And I demonstrated the Euler-Lagrange equations there happen to be the strain displacement relationships, which is also insanely incredible because I didn't go to the kinematic uh, derivations I did. I did it straight from the complementary principle of virtual work. Another exciting thing that we did there. And guess what? The boundary conditions that came out of the Euler-Lagrange equations were also telling us that the displacements need to be specified. So in other words, we've done some amazing things. From there, I further simplified the complementary principle of virtual work into the complementary theorem of potential energy. And now today I'm covering again the aspects of the complementary energy as it applies to the second Castigliano's theorem, which is quite extensively discussed in my book and also in my notes. So I hope this summary is clear to you. And with that said, I want to make sure that we are all in the same page. Let me first remind you what first Castigliano's theorem is. And the first Castigliano's theorem basically stated, so the first Castigliano, and I apologize for that, I always go, I prefer using a dark pencil. The first Castigliano theorem essentially stated that if I have a body of material and I have a fixed boundary of some kind and I apply a load, let's apply just a single load, Q1, and the deflection delta 1. What it's telling us is if I calculate the total potential energy, so calculate the total potential energy, then when I do that, I get pi equals, and of course I'll get the strain energy of the system. And clearly, the thing that Castigliano theorem did that was very clever, he stated that if I apply a load, the strain energy must depend on that deflection that you apply. So he just said, okay, delta 1, it depends on delta 1. I only applied a single one of them. Let's apply one more so you can see how that works, Q2, delta 2. So it depends on the strain energy will then depend on delta 1 and delta 2. That was the idea there. And then you also have the energy due to loads applied. Well, then you have the strain energy, and the energy due to loads applied is a minus of Q1 delta 1 minus Q2 delta 2. Very simple. And so now I can take the first variation of pi because we talked about how taking the first variation of pi renders the system in equilibrium. So why not take the first variation of pi? I apologize again. And here now pi, notice how pi, total potential energy, now depends on only delta 1 and delta 2. So now when I take the first variation of pi and set that equal to 0, I get that I have the derivative of pi respect to delta 1, del delta 1, plus the derivative of pi respect to delta 2, del delta 2. And so the derivative of pi respect to delta 1 is simply the derivative of u respect to delta 1. And I have this term here, so the derivative of that is minus q1 del delta 1 plus the derivative of u respect to delta 2 minus q2 del delta 2 equal to 0. And then I can use the fundamental lemma of calculus of variations. And since these variations are arbitrary, then each of these has to be equal to 0 independently because they're a linear independent summation here. So therefore, I get Castigliano's theorem, which is the derivative of u respect to delta 1 equals to q1, and the derivative of u respect to delta 2 equals q2. And so now I have two equations and two unknowns, so I can solve for the loads q1 and q2 if I were to apply deflections delta 1 and delta 2 at these particular points. And so that's how we developed the first Castigliano's theorem. And now I'm going to try to develop the second Castigliano's theorem. Now I'm going to apply the second Castigliano's theorem. Second Castigliano's theorem. And in today's lecture, what I want to do is examine the total complementary energy. I'll again examine the situation of a system with a load. And let me apply just two loads to make it simple. Q1 delta 1, Q2 delta 2. And now I'm going to examine the total. So here I examine the total potential energy. Now I'm going to examine. So let's go to second Castigliano's theorem now. I never like the red pen because the red pen makes me feel like somebody's grading me. Second Castigliano's theorem. And in second Castigliano's theorem, I'm going to now consider a situation, and I'm going to apply just two loads again, just to keep it simple. And I go into extensive discussions in my book. In the second Castigliano's theorem, I'm going to consider now the total complementary energy. And in this case, I'm going to say that I want now pi star to depend on the loads that I apply. In this case, Q1 and Q2. And I will now calculate the complementary strain energy. So U star respect to, I'm sorry about that, U star, which depends on Q1 and Q2, minus the potential energy due to loads applied, which is V star. But V star in our case is minus Q1 delta 1 minus Q2 delta 2. And so now I'll take the first variation of pi star, which is the partial of pi star respect to Q1 del Q1 plus pi star respect to Q2 del Q2. And now when I take the derivative, I simply get partial of U star respect to Q1 minus delta 1, check that out, del Q1 plus partial of U star respect to Q2 minus delta 2 del Q2 equals 0. And for any variations that I have there by the fundamental level of calculus of variation, then I get the partial of U star respect to Q1 equals delta 1, partial of U star respect to Q2 equals delta 2. Very exciting formulas, which I'm going to show and start demonstrating in a second. Very, very exciting. So let me get started with demonstrating this. And I think it will be a great demonstration on how this theory really works. So let's consider an axial bar example. And I'll consider this situation of a bar with an applied load somewhere here. And I'll say that distance is A and this distance is B. Okay? So what I could do then, I could remove this support. So because this is an indeterminate system. So let's remove that support and just say, okay, well, perhaps I have this situation now. And at this boundary where I remove the support, I will say, well, I can replace the support by a load Q, and there must be a deflection associated with that load Q, delta Q, let's call it. But we know that delta Q is zero. So we need to find Q somehow, and this is an indeterminate system. So let's calculate first. And the strategy really is going to be to find the strain energy of the system, the complementary version, and try to calculate something like this. So I know for a fact that the deflection is zero at this boundary, and so I just applied a load Q that replaces this boundary there, and hopefully we can get there. So the strategy is really to calculate the partial U star respect to Q and set that equal to delta Q, which is zero at that boundary. If I'm able to do that successfully, I may have been able to solve the problem. So in our problem, U star here is a triple integral of 1/2 sigma 1 epsilon 1 dV. But I want, when you're working with a complementary energy, you really want to have everything in terms of stress or load. Clearly, I had to change everything to load somehow. So the first step is to try to achieve that. And so let's start moving through that step. So if you recall, for an axial bar, epsilon 1 was equal to U1 prime. You can look it up. That's what we had for an axial bar. And so what I can do, I can say, okay, that's the integral from 0 to L, and I'll put the 1/2 here, double integral sigma 1 dA. And if you recall, epsilon 1 does not depend on dA at all, which is the reason that allows me to bring this outside of the um, dV. So let me just make this dV dA dx. And I'm going to use dx, so I don't have to use x1, I'll just leave it at x because we're clearly working in one dimensions here. So clearly, epsilon 1 does not depend on dA, so I can bring it outside and put it there, and which is exactly what I've done. And if you recall, this is N. That's the axial force. And if you forget anytime, you can look at the definition by looking at what this means. If I take the stress in a cross section and I were to integrate the stress over the cross section, that's clearly an axial force that's causing the bar to stretch. So now I'm able to now make the step and say, okay, well, this is 1/2 n epsilon 1 dx. The good news is that you should know that we will have gotten here. Why you should have known that? Well, because in 3D, the stress is conjugate to the strain. Well, in 1D axial bar, the axial force is conjugate to the axial strain. So it came out naturally. It came out naturally without me even trying hard. And so that is good news. Now I also know from the work we've done before that N is EA epsilon 1 So I can now solve for epsilon 1 which is N over EA. And if you forgot why N equals E11, EA E11, I can do it fairly quickly to remind you. So if you recall, N is the double integral of sigma 1 dA. But the sigma 1 is E in one-dimensional theory is E times epsilon 1 dA. And again, epsilon 1 does not depend on dA. I can bring it here. And E also is constant, so that doesn't matter. So I get a double integral of dA, E epsilon 1, and this is area, so I get EA epsilon 1. So I already showed you how to do that before, but I'm repeating it here again to help you understand the concepts. Now I can solve for epsilon 1 in terms of N and write the complementary strain energy only in terms of N. Because that's the whole point of the complementary energy. That's the way you want to write it. So 0 to L, 1/2 N, and I can plug this in there. So I get N divided by EA dx, and I get 1/2 0 to, and let me not put 0 to L because it could be x1 to x2, if you don't mind. It'll be cleaner that way. and then have 1/2 n squared. Oh, sorry again, having some computer issues. N squared over EA dx. So that's what I get for U star. Now what I can do now, I can do a cut here and a cut there. And that will allow me to then determine, basically, it's going to allow me to determine the strain, the complementary strain energy in each of those sections. So let's do a cut here first, cut A and then cut B. We'll do cut B and a cut A. So let's cut at a location A. And that'll give me an actual force that's internal to that section. Let's call it section 1, N1. Sorry, N section 1. Clearly in section 1, I must have, when I do a cut here, I must have that load is equilibrated by P and Q. So clearly N1 is P plus Q. And if I do a cut here, section B, then now I get a N2 for that section, so I'll call this section 1, this section 2, and I'm doing the cut there. So section 2 is going to be equal to only Q, just Q. Okay, because if I do a cut here, that's equilibrated by this load Q. And so then what I get now is U star equals, for section 1, the section 1 goes from 0 to A, and the load is P plus Q squared divided by EA dx, plus the integral from A to A plus B. For section 2, the load is Q, EA dx. And all I have to do now is find the derivative of U star respect to Q and set that equal to 0. Because we know there's no deflection on this end, and so I'm using Castigliano's theorem to force that. So I did forget a 1/2 here and 1/2 here, so very important miss. And what I want to do now, I want to go ahead and use Mathematica to solve it. Okay, so let's use Castigliano's theorem. Let's call this U star equals, and I have the integral, and I may not remember how to write the integral here, but we'll try it. Integrate is probably the word. Integrate, and I want to integrate, and I have a 1/2 that's everywhere, so let's just put it here. You don't have to put the 0.5. You don't have to put a star there. And then I have P plus Q squared divided by EA. And I'm integrating that from for x0 to A. And then I have another integral here that I had to do. And I could do it all by hand, but I'm just trying to show you how to do it in Mathematica really quickly, because it's more convenient to do it that way. Okay, let's see if this works. I personally haven't tried this before, so let's see if it works. Okay, hopefully it's correct. I hope it's correct. And so now I can find the derivative of U star respect to Q, and that should give me the deflection. Let's see if that's true. Let's call this deflection. So apparently it took the derivative and I found the deflection. Now I have to set the deflection equal to 0. So solve. So I have to solve that derivative and set it to 0. So I'm gonna set this equal to 0 and solve for Q. And then I should do, let's do 1/2 here so it doesn't carry the decimal points. Again, it's my first time trying this like this. I apologize if it's a little bit on the fly, but I think it'll be convenient for you to learn mathematics a little bit. Plus, oh, there you go. I got the load Q, which is in compression, and it's AP divided by A plus B. So we found Q using Mathematica really quickly. It saves you time. You don't have to do a lot of work, and the steps are usually the same. Very exciting because we found that Q, and I apologize for that again, Q equals minus PA divided by A plus B. And it makes sense. If A and B are equal, then the load P is applied in the middle, and so you will expect this to be Q equals P over 2. But if it's not, then you have to do more work. And then after you know Q, you can actually then determine let's say I want to know the deflection at point P. Let's say I want to know that deflection at point P. So all you have to do is substitute the formula for Q back into U star and then take the derivative of U star respect to P. So if I wanted to know, if we want to know the deflection at point P, simply calculate partial U star respect to P, and that will give you the deflection there. But you have to plug in the value of Q back into the formula. So yeah, let's go to a new example. I'm excited about this example because I want somebody to Google for me. Can somebody Google for me what is the deflection due to a cantilever load applied load P? What is the deflection there when you do that? Can somebody Google that for me and tell me what the answer is? And the length is L?
Sure.
So don't tell me. Tell me if it's correct what I'm going to write. It's going to be del equals PL cubed over 3I. Yes or no?
That's correct.
Yeah, yeah, that sounds right.
Right? This is exciting now. Let's do that. Let's derive that now. So well, we don't go ahead and derive that. And I'll start again with U star. And I want to have the triple integral there, 1/2 sigma 1, epsilon 1. It's a beam now, so I have to use order Bernoulli beam theory. I could use Timoshenko, but I'll use order Bernoulli beam theory for now. And recall that for order Bernoulli beam theory, epsilon 1 is x through a thickness, so let's call it z, u3 double prime. And it was only a function of x, where u3 is the deflection, this deflection here. Okay, that's u3, that deflection. So this is dv. And so now I want to turn everything into somehow, I want to get rid of epsilon 1 somehow. So that's the first step. So I want to examine then this carefully. Notice how I can bring this outside of the, so again, I'll do dv to be dA dx. And notice how part of epsilon 1 can be brought out. But I'll write everything out first. Sigma 1 d z. And I'll put in here u3 double prime x dA dx. This does not depend on dA. Here dA is dy dz dy. So this does not depend on that. So I can bring it over here. And so then I get this is equal to triple integral 1/2 let me take the triple integral out. Let me stop doing triple integrals. 1/2 double integral sigma 1 z d z dy, which is really dA, and then I have u3 double prime dx. If you recall, when you look at this very carefully, that's moment. That's really moment. And you can look at that more carefully by drawing a cross section that shows sigma 1, and you're going to see that that z times sigma 1 is really a moment arm. So that's moment. We defined that during order Bernoulli beam theory, so you should be very aware of what was done there. So therefore, I get this is equal from x1 to x2, 1/2 m u3 double prime. Again, m is energetically conjugate to the curvature. We saw that before. We demonstrated that before, and it was very exciting to see that. Just like in axial bar, n is energetically conjugate to the strain, axial strain, and in 3D, sigma 1 is conjugate to epsilon 1. Very similar, we're getting the idea that m is conjugate to E3 double prime. Very exciting. And so now I have m, and m is the double integral of sigma 1 z and d area, and sigma 1 is E epsilon 1 z dA, but epsilon 1 is z, you get z squared u3 double prime x dA, and again, E or u3 double prime do not depend on dA. Bring it outside, so you get E u3 double prime double integral of z squared dA. And if you look at your mechanics materials class or my YouTube lecture notes on static and strength of materials, this is a moment of inertia. So I get EI U3 double prime. So what I can do now is I can substitute it here, and I get 1/2 x1 to x2, and I get moment squared, and I apologize for that line there, so I'll continue here at the bottom. And that's complementary strain energy for this system. So now I'm ready. I'm ready to now apply this idea. Let's say I want to find the deflection of that endpoint. So very easy. So this is my beam. I have a load applied P. And okay, so let's do a cut there. And I'm going to look at this here. And I can draw my coordinate system any way I want because strain energy allows me to do that. So I'll take this as X. And guess what? I'll draw the cut there with a load applied P. And if this is X, then what is this moment? Moment must be equal to P times X. And I don't even care about the sign because guess what? U star is 1/2 integral m squared over EI, but m is squared, so I don't even care if the sign is right or wrong. I just put minus or plus, I don't care. And I get 1/2, and I have P squared, PX, this squared, all of that, EI dx. And I can integrate this from 0 to L, the length of the beam, and guess what? I get P squared x cubed over 6EI evaluated from 0 to L. Well, 0 to L gives you L cubed, so why not just write it down? I probably have an error. I don't, I'm correct. So if I find the partial, sorry about that. If I find the partial of U star respect to P, I should get the deflection here. So that's delta. So I'll get partial U star respect to P is PL cubed over 3EI. Isn't that exciting? Isn't that exciting? Or I'm the only one that's excited. I'm probably the only one that's excited, but who cares? I'm excited. It's a big deal. What if I want to find the load, the deflection? The load is applied here, but I want to find the deflection right in the middle. So I want to find the deflection from here to here. What is that? That's a question I want to ask. So pause the video at home and check it out. What will you do? Well, you got it right. Apply a fictitious force that's really zero for now, but just apply a fictitious force. And then what we want to do is find the strain energy. And once you find that in terms of P and Q, find the partial U star respect to Q. And since Q is fictitious, set Q equal to zero, and that will give me the deflection of Q. That'll be the strategy we're going to use. So why not do it now quickly? This is L, and I put the load in the middle. So I'll do a couple of cuts. I'll do a cut here in section 1 and section 2. So in section 1, I have a load P applied here, and it goes from, that's X. So if I cut here anywhere, I basically get a moment, and that moment is P times X. So that's for section 1. For section 2, I'll get this load Q here, this load P here, this is L half. I can define X going from here to here if I wanted to. And so I get a moment now again for portion 2. That moment for portion 2 can be found to be, for mechanics of materials, is Q times X plus P times L plus half plus X. I believe that's correct. Should be correct. Yeah, that's correct. So then U star becomes, so what is going to become? It's going to be the 1/2 integral m squared for portion 1 EI squared dx plus 1/2 portion 2 squared EI dx. And that's really 1/2 integral. And the first portion goes from 0 to L half x. So that's px squared over EI dx plus 1/2. And then now I have the second portion, which is 0 to L half also, because that's how I define x. Qx plus PL over 2 plus x squared over EI dx. So that's U star. So I'll just copy and paste this whole thing so I don't have to, like, it's basically the same formula. So the only thing changing is what's inside. So why not just go ahead and just write it down again? Integrate, and so what I want to integrate? I want to integrate px squared. So px squared over EI. This case is not EA, is EI. I'm cheating a little bit, but why not? I can do that because I'm the one teaching it. So Q times X plus, and I'll cheat again because I'm lazy. And that's okay to be lazy. L divided by 2 plus that, another parentheses, divided by EI. Very cool. Everything looks great. That integral goes from 0 to L half as well because of the way I define the X. And now I have U star. I took the derivative. Now evaluate U star. I'm sorry. Evaluate U star Q equals 0. Well, I didn't take the derivative yet, so I had to find the derivative, so I'll borrow this again. First, I need to find the derivative of U star respect to Q. That's the first step. And then once I do that, then I can set Q to 0. That's a step. So let's see what the deflection is at point Q. And that's the deflection at point Q due to that load applied. So we're going to look at another example yet. I think it's worth doing another example. And I think it shows how the approach really works. Now consider a different example. Let's say I have this crazy, the cool thing about this idea is that you can get fancy. You can look at beams that you couldn't look at before because, and please do not teach this trick to mechanics and materials students because then they're going to use it. And, we don't want to teach them the cool tricks. So this clamped. Say I have this beam and I apply a load, like that, F. Why not? And let's say that this is A, this A half, and obviously this 2A is like longer. I made it longer for some reason. I can actually find a deflection here, believe it or not. It looks crazy, but I can do it. I can do so I have this bar 1, this bar 2, this bar 3. I can start here. I can do a cut there first, see what happens. And I can choose a coordinate system that I want. I don't care. It doesn't matter. So this coordinate system X, I'll do that. So then what can I do? I can, so for bar 3, moment 3 is F times X. So bar 2, I can cut here now. And I can choose X to go that way now. I don't care. I can do it anywhere I want. So that's going to be, that this force F causes a moment, and that moment is going to be F times A half, and it's constant. And you can check it at home that's correct. And then bar 3, I have to cut it here. This is a little more difficult, but not too hard. Depending upon where you are in this beam, we could cut it so that I'm moving X this way, if you want. So that's a little more tricky, actually. So that's going to be, I still think it's going to be moment 3 is F times A half, I believe. And if I do a cut, let me draw the free body diagram. So I get a moment and a shear. So that moment is still F times A over 2, actually. So yeah, you're right. Chat is A half minus X. That's a correct moment due to that force F. And so now all you have to do is U star equals, and then you take the summation of from I equals 1 to 3, and you have all 3 of the energies. Actually, let me not do that. Write it 1 by 1, 1 half, 0 to A half. Moment 3 is Fx squared over EI dx plus 1 half, and then 0 to A, F A half squared EI dx plus 1 half integral 0 to A, and then that moment is going to change depending upon where you are. And so you're going to have F A half minus X squared over EI dx and then you find the derivative U star with respect to F to find the deflection at point F. So you don't have to do, it's very beautiful because you don't have to do a lot of work. In fact, I actually prefer doing it differently from what I did. Uh, if you don't mind, I want to do this moment differently from what I did. I actually don't like how I did it. I think the better way to do it, the simpler and cleaner to see with your own eyes, is to simply do a free body diagram of a cut here, but now looking from down up. I think it makes it much easier to look at it. So the first step is to find the reaction forces there. The reaction forces there at this boundary at the bottom, at point A, this point A, at point A, the reaction forces are F going that way, and then you have a counter moment. And the moment is going to be F A over 2. This is a cleaner way of doing it. And now you have this X here. So now the moment at any cut here that counteracts that is going to be F A over 2 plus F times X. It's a cleaner way of doing it. I think it's just much better at this cut. And so then I prefer that, if you don't mind, 0 to A now. And now I have, so I have F A half plus X squared E over I dx, and simply find this derivative and set that delta U star times derivative F equals delta F. That will give you the deflection, in fact, in that particular direction, which is quite exciting to be able to do that. I'm excited about this problem because it's not a problem that will be very easy to do with mechanics and materials, actually. It will take a lot more work to do. I want to show one more thing that's interesting. So say I have the same beam I discussed before, example 3 now, or example 4. You can get fancy now. You can do a load P and apply a couple moment. And so, okay, don't apply the couple moment. Say I want to find the rotation. Find the rotation at endpoint for the slope. So then just apply a couple moment C, which is fake, and C is 0. And then do a cut here again. If I do a cut there, then this moment counteracts that. So that's Px plus C. And now U star is 1/2 0 to L Px plus C squared over EI dx. Take the partial U star respect to C, set C equals 0, and that will give you the rotation theta at the end. We're looking at that end. And guess what? That's going to be the same thing you'll find in any book in mechanics and materials. They'll give you a list of formulas. It's going to be that. So very beautiful example. I like that example a lot. It's exciting. We can then look at more complicated problems. We can look at, let's do one more so you can see the application, and then I'll move to our optimization problem that's actually very exciting. So example 5. Example 5 is a beam that's fixed, and this is an indeterminate system. This is A, this is A. What I'm going to do, I'm going to take this boundary and I'm going to take it off. I'll take it off. If I take it off, we know there must be a reaction force R because it's a pin condition. But we know that deflection there at point R, at load R, is 0. We know that. So that's how you approach it. And now what you can do is you can do cuts. We can do a cut here and a cut here. Yeah, I mean, it will be, in essence, what I did before, but let's do it. Section 1, section 2, and then the moment in part 1 is just R times X. In part 2 is going to be, and that says in the middle, the load, so that's L ½. So I have R times L over 2 plus X minus P times X. And now all you have to do is calculate. So I did a cut there and a cut there. So if you're wondering, and so then I have the strain energy now, complementary strain energy. I apologize for the mistake in the words. 0 to L half Rx squared over EI dx plus 1 half L half. No, no, x equals 0. My convention is 0 to L half. And I have R times L half plus x minus px squared divided by EI dx. And now take the partial u star respect to R. Set R equal to 0, and then that will give you, I'm sorry, don't set R equal to 0. Do not do that. Set the deflection equal to 0 so you can find R, the reaction force. Very, very exciting. I won't do this because I already kind of did that in the previous example. Okay, an error was found in my calculations. This moment should be acting the other way. And should be acting this way. And that's a minus. And also, I said that this was bar 1, so I corrected that as bar 1. And here, I said this bar 1. And so I should have a minus sign there. So pay attention to that. I apologize for those watching this. And thank you for those that corrected me. I appreciate that very much. So I'm going to take, let's go next to the next example. And I apologize again, but there's a little mistake again. I apologize. The minus should go here. And that will correct everything. And you should be able to get the right answers that we want to see. Okay, so I'm going to go ahead and now look at a very interesting problem, but not, I won't solve it here. One other problems I will be talking about, but you could have an example problem where a problem where you have a beam that looks like a ring. And the cool thing about second Castigliano's theorem is if I apply a load P here and here, I should be able to determine the deflection at that point. And the trick there is to find the strain energy. But now from 0 to pi, and you're going to use a cylindrical coordinate system to get it done. But it's very doable, and it can be done, and is a very classical example that you may be able to find even online if you look it up. But what I want to do now is I want to examine a very, very interesting problem that has to do with optimization. Say I want to minimize the deflection of a beam when you apply a load, an end load. So let's say I have this beam and I want to apply a load P, and I want to find the minimum deflection delta P while keeping, we want to keep the volume constant. So in other words, how will you arrange the cross-sectional area? Let me actually say it more correctly. Minimize deflection, sorry. And what I want to do is minimize deflections given a volume V naught, find distribution of cross-sectional areas. Which is actually a very interesting problem. I think what I want to do, I want to consider a rectangular cross-section. So consider, in this example, you can do a circular one too. Consider a rectangular cross-section. This is a minimization, optimization problem. So, and we could consider a rectangular cross-section. If this is height h and the width is b, the moment of inertia becomes 1/12 bh cubed. I can also notice that area is B times H. And I wanna be able to parameterize everything so it's easy to follow, if you will. So what we don't call B, I apologize. I don't call B over H is alpha. So I'll parameterize it so it only depends really on one variable. If I do that, the inertia becomes 1 over 12 B times, well then I get, I'm sorry for the confusion, I get BH times H squared, and this is area A. Okay, so that's one way to do it. Regardless, I'm gonna continue here. So if I want to find the deflection at this point here, then that deflection is given by delta P equals the derivative U star respect to P, which is 1 over 12, 0 to L, P squared, X squared, because the moment is P times X. And I have here then EI, right, dx. And I want to minimize delta P. That's really my goal, is to minimize delta P. But I want to write this in a parameterized format, if you will, because it will make the calculations a little bit easier. So I call that A.
The class.
Okay, so I'm going to go ahead and show you that the moment of inertia can be expressed as 1 over 12 A squared, which is the cross-sectional area, divided by alpha. I believe that is correct. So 1 over 12, A squared is B squared H squared, and alpha is B over H. And so that's give you exactly 1 over 12 BH cubed. So the inertia can be written as 1 over 12 A squared alpha. I want to find A, and alpha is the ratio of B over H, which I'm keeping constant. So that way I have a prismatic beam, basically. So to accomplish that, since I want delta P to be minimized, I have to minimize this though, and I have to do that in such a way. Let's look at what I have now. So delta P now is a function of A, which I don't know. So therefore, delta P actually is a functional, which we never seen before. We haven't seen a problem like this before, but it's extremely interesting because we turn what is is almost like a fractal. Second Castigliano's theorem came from calculus variations. Now the formula for Castigliano's theorem now by itself became now a calculus variation problem, because I want to find the cross-sectional area A that minimizes delta P. But the problem is I need delta P to be minimized given a particular volume. So as a consequence, I have to come up with a new functional that's augmented using Lagrange multipliers. And that's going to look like this. J equals delta P plus lambda times the integral 0 to L AX dx minus the volume naught. Because I need to keep that volume the same. That becomes a constraint problem. I have to apply the constraint. That's my constraint here. Constraint to keep the volume V naught. It's very exciting because now I'm using second Castigliano's theorem to find the deflection in terms of P, but at the same time, I'm trying to find A that minimizes the deflection. And given the volume V naught, I want to know how the area gets distributed across this beam to achieve that, which is, I think is phenomenal. I think it's a phenomenal problem. And so what I can do now is I can write this one here, this term here, 0 to L, P squared, X squared. I'm going to substitute I for whatever I is, which is 12 here, over, so I have 12 alpha And then I have a squared at the bottom. The problem is that a squared now is a function, a is a function of x now. That's the problem. So I cannot take it outside of the integral anymore. Dx plus, and hopefully my steps are correct in what I've done, plus lambda, integral 0 to L, a of x, dx minus v naught. So that to me is very exciting because we came up with a functional now that depends on the area. And now what I can do is find the first version of J to figure out how to proceed forward. So while we don't do that, hopefully you can check my work to make sure everything looks appropriate here. These 2 cancels out with these 12, you get 6. And hopefully everything is accurate in everything I stated here in this particular formulation. So before I continue, let me simplify a little bit more if you don't mind. So J equals, now I have 6 p squared because p is constant, is a load applied at the very tip. Then I have alpha over E. So hopefully that's correct. So 6E and alpha, those come out really quickly, and that p squared comes out quickly. So I only have the integral from 0 to L, x squared over a of x squared, and hopefully that's also correct, dx minus lambda, and I have 0 to L, a of x minus v naught, sorry, that's a huge mistake, dx minus v naught. And why? Because this integral gives me volume, and I'm keeping the volume constant. I don't know what a of x is, which is my goal of finding that. And that will minimize the deflection somehow. So the first version of J now needs to be completed, which is really the derivative of J respect to A, del A equals 0, right? So that's how we do that. So let's now expand what del J is, and hopefully we can get there. So I have 6p squared alpha over E, and now I have this interesting integral that needs to be somehow be done. So I have to find that the derivative of this respect to A. So that's minus 2x squared. Hopefully that is correct. AX. And I don't stop writing A of x because we all know it's a function of x now. So A cubed. Hopefully that is correct and we don't have a mistake. And then now I have del of A there, which is quite cool to see that happening. Then I have plus, actually in the same integral I can combine. So I have minus, in the same integral I have minus lambda del A from here. I have a significant mistake. Let me explain what it is. So U star is really the integral of 0 to L p squared x squared EI dx. And I hope at home you can continue doing what I'm doing. The deflection at the very end, which is delta P, is equal to the partial U star respect to P. But that is going to be equal to, and there's a 1/2 here. The 1/2 cancels out. So you get 0 to L P x squared over EI dx. And that's an error that I have. And that, so therefore we need to fix this. There's no 1/2 there. There's no square there. No square there. No 1/2 there. Only a 12 here. And there shouldn't be a minus here. I don't know what that showed up. So I appreciate you guys keeping me in check because it's very easy to make mistakes. And so Here, this does not go there. That stays, I believe now it stays as 12. So that does not change. And I guess this is that, and that's 12. So we should be back in business. We should be okay now. I apologize for the number of mistakes I'm making, but it is important that you at least follow the steps. So I found that, um, and I also want to be careful because I try to combine too many things, and obviously, um, yeah, it's going to cause a mistake. So let's just be very patient with me. Let me bring this to the inside of the integral to keep everything very clean, so I can combine terms in an easy way. So that's 12p alpha e and del a, and then I have this term which is minus lambda del a. And so now I can close the parenthesis dx, and then I have, and I don't know why I put minus here, it should be plus. So again, a number of mistakes I'm making, but hopefully we can get through it together. Del lambda now, and then now I have the constraint. And this is equal to 0, the first version of j equals to 0. And so for any now, for any del a, what I'm stating then is that I have minus 2x squared divided by a cubed, 12p alpha e plus lambda is 0. Okay, and then I have this constraint, which is 0 to L. For any del lambda, I recover the constraint, which is this. So I recover the constraint, and the good news is I can solve for a now, and a of x now becomes simply, and we can check it together as a team, 24p times alpha x squared divided by e lambda. I'm kind of doing that by memory at the moment. So I'm kind of looking at everything here. I have to do a cube root. Right, that looks correct. Lambda goes to the denominator. E stays in the denominator. That's 24. P alpha x squared, all that has to be 1 cube root. So this looks correct to me. I'm very excited about this particular problem. I apologize for keep getting excited about this problem, but it's actually a very exciting problem. It's not my fault that we're solving a very exciting problem, in my opinion. Now I'll take this. Guess what? Guess what? This is an amazing application of this. Now I'll take this and plug it in here. And I know V naught. V naught is given to you. So I'm going to take that integral 0 to L. And now I'll integrate it over x. So I have 24 p alpha e over lambda 1 cubed. And I have x to the 2/3 dx, and I'll integrate this over the volume. And when you do that, that's going to give you a way of calculating lambda, because lambda is not known at the moment. And once you know lambda, you plug it back in here and you get a of x. So when you do that, you're going to find that a of x is going to be a constant times x to the 2/3 is what you're going to find, which is extremely amazing. It's telling us that for me to minimize that deflection, the cross section has to look like something like this. And it's going to go to a point, basically. And the curve here is given by x to the 2/3, which, sorry, times a constant, of course. So the cross-sectional area there is going to become that. To me, that's an exciting problem because it shows the use of optimization, calculus of variations, to show that if I apply load P, I can minimize the deflection, keeping the volume constant, and to make that happen, the area has to be distributed in that manner.